All right, so I'll be talking about evidence synthesis. And first, just to give you a little bit of a general introduction, what we're talking about when I say evidence synthesis within the context of Odyssey. Some of you have seen me present this before, but I think this is good to go over. What we're talking about, of course, in Odyssey is usually a network of databases, a distributed research network, such as the Odyssey Evidence Network, where we have multiple sites that have patient data, for example, EHRs or claims data. And this is patient level data that cannot be shared, but luckily we all adhere to the OMOP common data model. And what that allows us to do is any of the sites in Odyssey could decide to lead a study, develop analysis code locally, for example, using Strategos, distribute that code to all the participants. They can then run it against their data and then share back aggregate data, which is not patient level data, so is therefore safe to be shared back. And then the coordinating site can synthesize those results to answer any question. What we'll be focusing on today, as Patrick already mentioned, is specifically when we're doing estimation studies. So when we're trying to estimate a causal effect, but as Patrick also mentioned, this same process can also be applied to any other type of study, and especially like characterization studies. It's still a very much an open question how to do this appropriately. As I'll show you for estimation, we found it's actually quite challenging and interesting problem to work on. So I also would encourage anybody who's interested to work on this methods question to pick that up and reach out if you want to collaborate with us. For estimation, so one example of a now pretty old study where we did this is we ran this study on angioedema and levetiracetam a while back, and so every site produced a estimate, in this case a hazard ratio with a confidence interval, and then we simply combined the hazard ratios using a random effects meta-analysis to produce a summary estimate. But there is a bit of a challenge when we just take the standard of off-the-shelf random effects meta-analysis, in this case Dorsimoni and Laird. Oh, sorry. Why would we just share only this bit and not more detailed information? Well, we cannot share patient level data, so we certainly can't just give you our data sets of one patient per row. We usually have things like propensity scores, stratified time to event, or conditional Poisson regression. So there's also not just a 2x2 table that we can share that is people exposed, unexposed, and with the event and without the event, because that doesn't exist. We have that at a very granular level, usually for different time to events. So what we do tend to share is point estimates and standard errors, or basically the confidence intervals. But there, a problem that we have encountered in the past is that often our counts of the outcome are very small. So we have lots of data. Like in this example, we have 22,000 people in the target and 130,000 people in the comparator, but we only have 3 people who have the outcome in the target and 25 in the comparator. And that's what I would call a small count. It's the number of outcomes. And what then happens is that normally when you say I have a point estimate with a confidence interval, you're assuming that the likelihood of where the true hazard ratio is normally distributed, here indicated by this dashed line, where in fact the actual distribution could be a little bit off from this normal distribution. It actually could be far off, as I'm already showing you here. There's a disagreement between the two lines. And this is actually real data from a real study, so this is not made up. This problem is actually even worse if one of the arms, for example, your target or comparator, has 0 outcomes, because now your likelihood distribution actually doesn't have a peak. It doesn't have, you don't have a point estimate. You don't really have a confidence interval, but there is certainly information here. So in this case, like there are 0 people with the outcome in the target group and 10 in the comparator group. That is telling us something, that it's maybe actually, as the curve shows, it's more likely that the hazard ratio is low than that it's high. And so the solution that we published a while back is, I would say, pretty straightforward. Instead of this idea of just a point estimate with a confidence interval, why don't we actually just communicate the full shape of that likelihood curve? Our current best practice is what we call adaptive grid, where we just basically sample the likelihood at various hazard ratios. We're working on a new approach that actually seems to be more efficient than this approach, but currently this is the best practice that we're using. And then the idea is that every site just communicates this shape of the curve instead of the point estimate, just the point estimates and the standard errors. The evidence synthesis package, the R package, actually implements this whole approach, and other Hades packages such as cohort method and self-controlled case series make sure that they actually output these likelihood curves as well as just the point estimate and the confidence interval. Afterwards, once you have these curves, there are two ways basically in which you can combine them, synthesize them into a single estimate. One is the fixed effects model, where you assume that basically the effect is the same across all data sites, which in our situation is hardly ever realistic. Like, databases tend to have very different populations, so you might expect different effect sizes across the network. And so we usually use a random effects model. And here we have a bit of a problem that we might be underpowered for random effects models, getting a little bit too maybe into the weeds. So we use a Bayesian random effects model, where we have a prior on the random effects standard deviation, and then we basically update that with the data that we get. And for that, we use the Beast Markov chain Monte Carlo engine. Anyway, long story short, so what then happens is, before, things would be like you see on the left. If you just use ordinary random effects meta-analysis without using these curves, then you basically assume normality, as I'm showing you here. So for every site, we run the analysis, say Strategos, and we get a point estimate and a confidence interval. And like I said, we assume normality. Some sites we actually don't have non-zero counts in every arm, so we might get no estimate, even though there might be data. And then we summarize that and we get a result. But now if we use this approach of adaptive grids or likelihood curves, we actually see that some of these sites, even though they had a zero count and we couldn't produce a hazard ratio estimate, there's still information there. In this case, all of these sites actually say that it's more likely for the hazard ratio to be higher. And so now if we integrate that information, synthesize that, we actually see that our estimate, our summary estimate, is very different than if we don't take into account these basically these small counts. So this is basically arguing that we need this approach, especially in Odyssey, where we tend to look at, well, we have multiple sites to begin with, where we can run the same analysis and produce these curves, but also where we do run into this problem quite often, where the outcome counts are quite low, meaning like single or double digits. This does mean that it's if we integrate all of this into our current workflow, this gets to be a little bit complicated. So what we see is that in a specific database, we produce our estimates of interest. As you remember from earlier presentations, we apply diagnostics to see whether or not we actually can unblind these estimates. We do the same thing for negative controls, and then we can produce a calibrated estimate that is unblinded within a specific database. But now if we want to do this across the network, then these unblinded estimates go through evidence synthesis. And then we have a summary unblinded estimate across the network. but only the sites where we pass diagnostics actually contribute to this synthesis. We do the same thing for the negative controls. And we do this separately because now we do a new calibration step using the synthesized negative controls to calibrate the summary estimates for the outcome of interest. And then we have unblinded and calibrated summary estimates across the network. So there are quite a few moving parts to get to this point. And so now when you look at the plots that we produce, there's actually quite a lot of differences between the estimates that we get from the databases and the estimates that we have across the network. One difference is there can be different calibration. The databases, we might not actually have a point estimate, as I showed earlier, if there's a zero count in one of the arms, so that might be a difference because that database would still contribute to the synthesized result. And we use a random effects model. So all in all, it's a complicated machinery, but I do think it's the right way to approach this, as I tried to explain. So how does this actually work in practice? So when you do a study, so suppose you have several sites that are participating, you are the study coordinator, you design your study that produces the JSON input for Strategos, you send that probably through a GitHub repo in Odyssey Studies to the different sites. The sites execute this on their data and produce CSV files with summary statistics, including the likelihood profiles. Those get sent back to the coordinating site. Initially, those results are uploaded into results database and can be viewed through a Shiny app. And then comes the evidence synthesis step. You actually have to separately design the evidence synthesis, although it's pretty much always the same, as I'll show in a minute. That leads to a JSON file that you don't have to communicate with anybody. You just run it locally in Strategos. It uses the results stored in the results database. You get new CSV files that you upload, and now you can also see those results in the Shiny viewer. And just briefly, the code for basically specifying the evidence synthesis and running it in Strategos. I've hyperlinked it here. I'm not going to go into detail, just to make the point that this is pretty much always the same. We usually don't have to change this because this is just saying we run it on a Bayesian random effects model using adaptive grid on cohort method, and we run the same thing on the SCCS. We combine that, and this takes care of all of these steps that I showed earlier. So only including unblinded estimates, performing the calibration again at the meta-analysis level and producing the results. And with that, I want to hand it over to Jan.
Yeah, thank you, Martijn. Let me share my screen. Can you see my screen?
Yep, we see it.
Great. So I think Martijn has already given an introduction about how do we synthesize the evidence and generate results. So here I'm going to talk about considerations that safeguard against the false positive findings. One of the key innovations in the Odyssey, as you know, is the use of negative control outcomes to calibrate the p-values and to make sure the results are reproducible and the evidence are reliable. So I'm going to just refer back to some classical figures, and I think many of you have seen this before. So this is a figure taken from these papers published by the Odyssey researchers. We basically here we have a large number of causal estimates estimating the causal effect of some intervention on some outcomes. But here we just lump them all together. So we have like here close to 12,000 estimates. And in this case, we have the prior knowledge that the outcomes are likely to be unrelated with the exposure. So in this case, we call this outcome, these estimates are the null estimates. So in other words, we have approximate underlying truth. So when this is the case, if we plot this in this so-called funnel plot, So for those of you who are not familiar with the funnel plot, this is the funnel plot that basically you plot the effect size estimate. In this case, is a hazard ratio against the standard error. And so one of the key features is that for funnel plot, if you put, say, higher, more precise estimate at the bottom, less precise estimate at the top. So typically you will have something like a funnel, like a final shape. You have more variabilities on the top, less variability in the bottom, right? That's one thing we would know. And the other thing we would know is that if all the outcomes are null outcomes, meaning that they are not associated with the exposure of interest. So 95% of them, 95% of the confidence interval should be covering 0. In other words, if you rely on p-values, about 5% of them will reject the null hypothesis of hazard ratio equal to 1 at the nominal level of 0.05. So, but in this case, what we find is that we have actually about 15% of confidence interval excluding 1. So this is known as excessive or inflated type 1 error. So so this is as you can see here, this dashed line here basically is characterizing for each given standard error, what would be or the size of the study, what would be the possible range that not excluding 1. So you have, in this case, we actually have about 7.5% of the estimate being either on the left-hand side of the dashed line or the right-hand side of the dashed line. So so one way to deal with this inflated type 1 error is to use the concept of negative control. So a negative control pair consists of 2 random variables. Typically, is a drug and the outcome. When we talk about negative control, it's always under some context. The simplest case is basically exposure outcome combination. And in this case, the reason we call it negative, it means that there's no causal relationship between the 2 entities. So in a set of the literature, in the Odyssey community, we established that using negative control, we can detect systematic bias. Here is a systematic bias as a totality is comprised of biases due to unmeasured confounding, or selection bias, or some measurement error, so-called information bias, altogether. So those biases could be detected by these negative control pairs. The other utility of this, in the paper published by Martijn a few years ago, is the p-value calibration. So basically, we can use negative control pairs to adjust p-values and make the test of the causal relationship to be more reliable. So so the procedure is the following. So for typically in the Odyssey context, we recommend people to consider a few dozen NCO rather than relying on 1, because in reality, how would we know for sure that there's no causal relationship between exposure and outcome? We don't want to put all the eggs in one basket, right? So we want to consider a set of the NCOs. And in this case, for example, if we denote Yj as the estimated log effect size, for example, log hazard ratio or log relative risk, and we can use funnel plot again to visualize the NCO distributions. And then using NCO, empirical NCO, we can estimate this their distribution. And in reality, as you know, we know the true NCO should have mean 0, but in reality, this distribution of theta, this Yj, indicated by random effect theta j, so may not have a mean of 0. So this mu basically characterize the systematic error, specifically associated with this particular data set and the particular causal inference pipeline. And this tau square basically reflects what is the so-called the intrinsic variation across different NCOs in terms of their causal estimate. So once we estimate this mu and the tau square, we can, for any hypothesis of interest, so the proposed p-value calibration procedure is fairly straightforward. Basically, this is the new estimate, the point estimate. Suppose you investigate the association between taking the GLP-1 medication and the outcome, say heart failure, right? So you can estimate some causal effect, but you want to using those NCOs, you can actually use this NCO to calibrate the corresponding p-values. So this is the p-value calculation formula. Basically, you subtract this y, your estimate by the estimated systematic error. This is quantified by the set of NCOs you have. And then the variance is also calibrated by your standard error, square of your standard error, plus this the intrinsic heterogeneity across different NCOs. So I know in some literature, people have been criticizing, okay, adding this tau square, adding this, we are making this study underpowered in some studies, like a pharmacoepi study. So it's kind of, in terms of the drug adverse event, it's kind of in favor of not finding, in favor of the studies in terms of not identifying any adverse event. But in fact, this is exactly what we need. So if you don't calibrate, you wouldn't get the, you would get a more false positive findings. And if you over-calibrate, you will get too many false negative findings. So in the later slides, I will show this is indeed what we need. And this is indeed necessary. So now let's take a look at the settings that we have a multi-site, evidence synthesis exercise. This is usually the case in the Odyssey, right? We want to collaborate. We want to not only pool results together to gain higher statistical efficiency, but we will also want to characterize the heterogeneity of the different outcomes across different studies. So in this case, we have to introduce two double index notations. So we have K indicate a particular data partner, and J is a particular NCO. And we just at high level, we need to actually consider two types of variations. We have, for the site one, suppose we only have 4 NCO. Normally, we at least recommend, say, 40 NCOs to calibrate. Just to keep it simple, say, we have 4 NCOs within site 1, 4 NCOs in the site 2, and 4 in site 3. And this across different estimates, you can, if you generate this plot, you can characterize this so-called between outcome variance. And across different studies, there's also a between study heterogeneity. So there's basically 2 layers of heterogeneity that we need to truly account for. And I think this figure makes all this explanation more intuitive. Basically, for each data partner, you generate one row, which is the this can be a point estimate and a standard error, or it can be some type of the likelihood when you have the rare disease and a rare exposure. So, but the point here is that for each site we have a point estimate, a standard error, and for each of the NCOs, right? Here we have a J NCO, and you have the new outcome of interest. And then across the sites, you basically have a big table like this. Using our profile likelihood approach, combining what we recommend is that for each given NCO, for each J, we can first aggregate, and you get aggregated estimator. Typically, we'll have a smaller standard error. The likelihood profile would be more spiky than the individual likelihood. And notice that this actually allows some of the likelihood to be completely monotonic. In that case, the point estimate wouldn't be available. So we will still incorporate those evidence for the causal effect. And for each of the NCOs, we can aggregate, and then we can estimate the overall distribution across those NCOs. So in this case, it's also the familiar notation. The mu indicates the overall systematic error identified by multiple sites and multiple NCOs. And this omega square characterizes the intrinsic heterogeneity across different NCO causal estimates. And then we can use this to calibrate the results for the outcome of interest. For the outcome of interest, we will also use this aggregation approach that Martijn talked about to aggregate. And then you can calibrate using the p-value calibration formula. Basically, subtract this theta prime by mu and divide it by the square of the standard error plus omega square as a way to truthfully reflect the intrinsic heterogeneity across NCOs. Let me just give you some example. Again, this is not simulated data. This is the data from the Legend type 2 diabetes study published at the JAC. So here we actually have 5 sites, and we have a list of about 40 NCO chosen here. And if you look within each site, you can see that the coverage of the confidence interval, excluding 1, is not close to 95%. In this case, there's 90% for site 1, site A, 90% for site B, and here is poorly only 40% for site C, 100% for site D. So this is the case that you are being too conservative, right? So this is the case that you are being, So this is a case that you are being, the confidence interval is this is indeed too conservative. And this is the case that you actually have very long confidence interval. So 100% coverage, and then this is only 90% coverage. So as you can see, they are all not close to the 95% confidence coverage nominal level. And across the sites, there is a huge amount of heterogeneity in terms of the coverage, right? That's one thing we capture. But we want to put this in the table so that we can analyze them together and then draw strengths from this collaboration. So one way to, as a diagnosis, one way to diagnose whether we are doing a good job in calibration is actually to plot the empirical coverage, which is a fraction of the p-value less than a given nominal level. This alpha can go from 0 to 1 versus the theoretical level. So under the null hypothesis, if all these NCOs are truly NCOs, then the p-value should follow. It's well known is they should follow a uniform distribution. So basically, this theoretical p-value is just calculating from a uniform distribution. And in this case, as you can see, the without doing calibration, our empirical p-values, in terms of the fractions, is quite off compared to this 45-degree line. This is our gold standard. And if we are doing this multi-site calibration, as we talked about here, turns out that it can draw the strengths from this multi-site modeling and multi-site collaboration. They are very close to the true the theoretical line, which is this 45-degree gray line. And putting in this concrete setting, so we the coverage of the confidence interval is about 94.6%, including 1. Okay, now back to this study. So this is actually the list of outcome of interest. So we applied this multi-site NCO calibration. So those are the NCO calibrated relative risk. And here just to highlight a few outcome of interest. So those are the final estimate. So in summary, I think it's really necessary to consider when we do multi-site study. It's necessary to consider the NCO calibration, and the procedure is as simple as the procedure that Martijn introduced. So you just need to treat each negative outcome as a new outcome, and then you can repeat the procedure. This can be done simultaneously. And then at the end of the day, you pass all the results to the lead site. And the lead site need to look at this table and use a formula that we derived to do this multi-site p-value calibration. So this will be a paper forthcoming. We will post this paper to the archive as well. So I think that's all from me. So thank you. So we are open for the questions.
Yeah, absolutely. We have about 10 minutes here. So first I want to thank Yong and Martijn for that excellent presentation, the work they put into it. We'll just open it for questions. It can be put in the chat, but you know, it might be easier if people want to raise hands and just share. All right, go ahead, Patrick.
Thank you, Martijn and Yong, for these presentations. This was really excellent. One of the things I'm observing in the literature still, even actually just this week, I saw yet another example of network studies that are being done where they choose to report studies just based on only the composite of the network. And so they don't report site-specific estimates. They only report the composite. And they don't report any sort of notion of whether or not there was the existence of heterogeneity. And it seems to me one of the real value propositions we get from having our network is being able to observe the diversity of estimates we see across the network and being able to use heterogeneity as a tool to understand whether what we found is robust or not. So I wonder whether both of you could just comment on what we're really learning from a meta-analysis as it relates to representing variation that's due to heterogeneity and why that might be a preferred approach to just aggregating or pooling data or treating the network like it's one source.
So, Martijn, do you want to?
Yeah, I can go first. Yeah, no. So you're absolutely right, Patrick, that I think there's a lot of value in the heterogeneity. One of the things we do tend to do is if we try to get a single answer for a question, we tend to focus on the meta-analytic estimate, which I think is the right thing to do. But then to understand more about that estimate, we do need to consider the heterogeneity. And we actually have a diagnostic that says that if heterogeneity is too big, then we should not be looking at the result, because then you have these weird things where some estimates are over here, some estimates are over there, and our meta-analysis is there, which is not something that's observed anywhere. And so knowing that there is this heterogeneity is definitely a key part of the picture. And I mean, in general, I'm of course biased, but I think also the fact that we do these studies across all these sites is a large strength of the Odyssey studies, where if we do observe heterogeneity, that's like a very important piece of information, rather than other people might just have one of the points in the plot. Yong, did you want to add something?
Yeah, yes. So I've been working on the meta-analysis systematic review for almost 20 years. So I feel historically people view heterogeneity is some negative nuance, but I think as the field has moved on and people now realize heterogeneity is actually an opportunity. It's an opportunity for us to understand the true differences between the studies, and also heterogeneity, those diagnoses or the visualization or the metrics, for example, like I-square, developed by Julia Hingis and colleagues. So those things can help us to do some detective job. For example, across these sites, for this particular NCO, if you see this tau square is 10 times bigger than any other tau square, that actually will give us some information. Maybe something, is going on with this NCO. Maybe across different sites there are some group level heterogeneity. In some studies, of course we need to pre-specify the detective job that we want to do. Otherwise, it would be a lot of post hoc analysis and cherry picking. But typically for meta-analysis, traditional meta-analysis, we always pre-specify the subgroups, subgroup analysis or meta-regression we want to do, which will help us to look for more homogeneous heterogeneity within the subgroup. But there's a finite number of studies you could specify. Again, I think those heterogeneity, they are both necessary, reflecting the intrinsic differences across different NCOs, including the outcome of interest. And they are also opportunity for us to understand better what's going on. So.
Great, thank you. Question in the, Martijn answered. I know some people don't get the chat, so I'm just going to ask you, Martijn, to answer. Will the evidence synthesis R package help with NCO pairs p-value adjustment?
Yeah, so as I've tried to answer in the chat also, so the evidence synthesis package itself is a very statistically oriented package. So it does the basically the synthesis using the Bayesian random effects model and the likelihood profiles. But there is the evidence synthesis module inside of Strategos, which actually uses the evidence synthesis package. And that module is the thing that does all the fancy synthesizing negative controls separately and then reapplying the calibration at that level. So I highly recommend for just users of evidence synthesis to use the Strategos module. And if you're interested in the nitty-gritty methods, details, and the methods research, then go to the actual evidence synthesis package.
Richard?
Can you hear me okay?
Yes.
Yep.
Awesome. Fantastic work. I've always admired this work that you guys are doing here. My question is, it seems like because you're doing only adjustment of the estimates using negative controls, which implies, I think, a broadening or an expanding of the confidence intervals around the point estimate. So if you have something that's a small positive effect, if you're only using the negative controls, would that possibly hide an actual positive effect? Because you're just, you're expanding, your only thing that you're doing is expanding the confidence intervals. Are you, if so, is there any possibility to possibly use some positive controls in addition to some negative controls to see how that balances out the adjustment? And I think an example of this would be like with the fluoroquinolone aortic aneurysm dissection study that you all published. It looked like that was, very good use of negative controls, but there were no positive controls in that study. So there might have been a small effect size, maybe, that you might have, possibly just kind of washed out with this adjustment. Just want to know what your thoughts were on that.
So just to be clear, so even with negative controls, you could have something that wasn't significant before be significant after calibration. Like if all your negative controls show that there is a negative bias, then the overall adjustment wouldn't just be to make confidence intervals wider, but it could actually move your point estimate upwards. That being said, usually what happens is it makes confidence intervals wider. But that, I think, is just a proper reflection of how much uncertainty there is. So a uncalibrated confidence interval just captures your uncertainty due to random error, and then the calibrated confidence interval just makes it wider to account for your uncertainty. So it's, I prefer not to talk about, first you see it, now you don't, because then you're talking about like p-values and using them for hypothesis testing, and not rejecting the null doesn't mean all of a sudden that the null became true. It's just that you lost power. We have looked at positive controls in the past. They're just extremely tricky for several reasons. First of all, there are not that many that we all agree are positive. If we do agree that they're positive, then there is no real hard evidence on exactly what the magnitude is, and actually will be probably different for different populations. And then the third one that we also see very often is if we all agree it's positive, then the doctors know this, and then they will do like horrible things like mitigate the risk. So if we give something that's known to have a side effect, they will make sure that the person doesn't get the side effect, and then that's bad for us because then the negative control or the positive control actually no longer is positive because we don't see the effect anymore. So yeah, I hope that answers your question.
Yeah, can I add a point? So
Yeah.
So yeah, I think Richard, this is a great question. So really, we actually have some newer results coming soon. We found that as Martin said, not always the confidence will get bigger because tau square theoretically can be 0. In a lot of cases, it can be 0. It's a moment estimate, it can be 0 quite a number of times. The other point is that if you could move your point estimate to be a positive side or the negative side. So, it's not always we make the significant study or positive association disappear. The other point we found is that actually I can show you very quickly some results from our most recent investigation in terms of the p-value calibration. Actually, there is an efficiency consideration. We have a chapter section about the adjustment for efficiency. So if you consider a scenario, you don't adjust the confounder at all, you can always pretend not adjusting, or you only adjust a little bit, just 3 confounders, 6 confounders, and so on. Actually, there is a good efficiency gain for this calibrated result versus uncalibrated. So here the y-axis is a confidence interval length. As you can see, if you are doing a better and better job adjusting the observed confounder, the efficiency loss in terms of the confidence interval length is becoming smaller and smaller. So this is actually a very important lesson for us to learn. Not only adjusting measured confounder, a measured confounder using NCO is important, but also, as we know, we should incorporate as many measured confounder as possible in a reasonable way. So